Okay. Can you confirm me that my screen is visible to all of you?
Yes, sir.
Thank you. Okay, so let us recap a little bit whatever we have discussed. So we have started very interesting things, and then probably the last topic of our syllabus. However, there was one more thing regarding the alternative fuels. Let us see. I can hold at least one class on the alternative fuels also. But last class we are discussing about the emissions. We discussed about there are different categories of the emissions, and then after that we defined it that whatever the emissions coming out from the engine exhaust, it has been divided into the two parts. One is called regulated emissions, and another is called unregulated emissions, and what is the effect of the pollutants on the human health or as well as the environment. Then we also discuss about the emissions legislations, the procedure, how to do the testing. Yeah, in the that testing, I just forget to tell you that um, we have in India, Pune, that is a government organization, is called ARI, okay, All India Automotive Research Association, something like that. I just forget the name. That organization is responsible to do the testing for emissions. If ARI is going to um, give the certifications that yes, your vehicle is fulfilling the current emissions legislation, then you will be in the positions to do the testing. It's not like that automotive industry will do their certifications by self and then they will launch the car. It's not like that. There is a proper government agencies that in Pune, and the automotive company has to get the certifications from them. In fact, you have to take your one of the vehicles or whatever the demands, and then the actual testing is going to be there, and whatever the results are going to get at that point, it's going to be the final decision. Then we also discuss about the history of our particularly the Indian history, that how the different Bharat norms, Bharat stage norms has been evolved over the 2 decades, and currently we are having Bharat stage 6, and then we discussed about the approximate range of the different regulated pollutants. All these things we discussed in the last class. Today, let us start. Okay, so in a very short format, we will try to understand that what is the reason to form these emissions. Okay, so one of the major pollutants that we have discussed in the previous section is the NOx. NOx, what is it? NOx? NOx is the combination of NO plus NO2. It is the oxides of nitrogen, NO plus NO2, in which NO concentration is dominating. It depends upon the kind of the engine. Okay. At this point, it's better to clarify also. SI engine, the the NOx that is coming out from the SI engine, it is mostly NO. Very few percentage of NO2 will be present in the NOx that is coming out from the SI engine. Okay. However, we cannot neglect it. We cannot neglect it in terms of in the CI engine, where the NO2 concentration has a significant value. However, it will be always less than the NO, or we can say that NO2 by NOx can go up to maximum 30%. So it is a considerable amount that we cannot neglect NO2. We cannot say that NOx is the only NO in case of CI engine, but in SI engine, you can say that NOx is nothing but NO. So how NO formation takes place? That's the most important thing. In our very simple analysis of the combustion, we assume at that point that nitrogen present in the air that is used for the oxidizer doesn't participate into the combustion, and then the whole nitrogen comes out into the product form. But it's not like that. The environment inside the combustion chamber, environment in terms of the temperature, is favorable, or it is critical above the critical values where nitrogen will participate into the combustion. And what happens that when the work temperature inside the combustion chamber goes beyond the values and there is a presence of oxygen, then nitrogen will oxidized and it will form the NO. So there is a two critical requirements. There are two critical things that is need to be fulfilled. Then the NO formation will take place. One is the temperature inside the combustion chamber, and at that temperature, oxygen availability must be there. Temperature alone, it doesn't mean that NOx will form. It has to be, oxygen must be also present. Now the temperature, since if the temperature inside the combustion chamber is more than something around 2000 Kelvin, okay, and if at that temperature, if oxygen is also present, then nitrogen will react with the oxygen atom and it will form the NO and NO2. So that's it. That condition has to be fulfilled. So the temperature is always in the IC engine. The temperature is no doubt it is up to the limit or beyond the 2000 Kelvin, and the oxygen availability is also going to be there. How in SI engine we can say that oxygen availability is slightly less because it is always runs towards the stoichiometric combustion mixture, but in CI engine that is always runs towards the linear side, linear mixtures. So oxygen availability is not a problem. So if you want to reduce the NO formation, NOx formation inside the combustion chamber itself, then you need to handle it in such a way that temperature should not achieve the critical values, or what is the oxygen concentration at that time. So if you play with these two things, then there is possibility to reduce the formation of NO itself in the combustion chamber itself. Okay, so that's the two things. This is a temperature dependent NOx is the temperature dependent phenomena, and the oxygen availability. Both, always remember, both condition has to be satisfied. Alone temperature is not sufficient to form the NO. Similarly, CO. So fuel is a hydrocarbon, and if there is a incomplete combustion because of any reason, okay, then what will happen? It will form the CO. It is an intermediate product, okay. But if the CO can get the oxygen, then it will be converted into the CO2. So what happens that particularly in the rich air fuel mixture, there is a inavailability of the oxygen, and then in that condition, what will happen? That CO will not find enough oxygen to further oxidized into CO2, and then CO will come out into the exhaust, and that will be the problematic, or that will be the pollutants. Now, if you remember in the last class, I told that CO is not considered as a too much, or we can say that it's not a too much problem for the CI engine. The reason is that even if in the rich air fuel mixture, okay, CO forms, then what happens that since the in diesel engine there we have a penalty of oxygen, okay, we have oxygen availability, so CO will find oxygen and it will convert into the CO2. So therefore the CO concentration in the diesel engine is very less, is very less, and and therefore it's a insignificant kind of the pollutants we may say in case of the diesel engine, but that is not the case in the SI engine combustion, because SI engine, as I told you, there is always or very close to the stoichiometric mixtures or even slightly rich mixtures runs. So there the oxygen availability is a problem. So if because of the any region, if the CO forms, then chances to get it convert further into the CO2 is less, and then therefore the CO emissions will come out, and there is enough concentration where we have to take care very carefully so that not too much CO can go out into the atmosphere. As far as the hydrocarbon emission is concerned, it is really very bad, because hydrocarbon or CO emission is directly indicating you the insufficient or income. Sorry, it is indicating you the quality of the combustion. If the CO emission is more, what does it mean? It means the combustion is not taking place efficiently. If it will take efficiently, then all the hydrogen and carbon present in the fuel, it is going to be the oxidized into the CO2 and H2. So but HC or hydrocarbon emissions is significant in both kind of the engine SI and CI. If we anyway, we are not going to into details of the reasons why it forms into the why it forms. The only thing is that what I would say, you will find it out that any fuels, if it is going to escape from the primary combustion, okay, because of the any reason, then what will happen that fuel or part of the fuel will have a higher chance to come out in the exhaust manifold and forms the pollutants as a total hydrocarbon emissions. Now the question arises here that why the part of the fuels may escape? Why the reason? What is the reason that it will be escaped from the primary combustion? The reason might be there are several small volumes in the combustion chamber. Several small volumes. If you remember, in the beginning of the semester when we were discussing about the different parts of the engine and the combustion chamber, realize that the shape of the piston. From the top, one thing is we have already known that diameter of the piston is slightly lesser than the diameter of your cylinder, and the first ring that is compression ring is after the gap, at a certain height below from the top of the piston. So surrounding that piston, there is a very small volume. That is a small volume. So what happens? I hope that the way I'm explaining it is clear in your mind. That I'm trying to explain that there is a small volume. One of the small volume I'm trying to explain you that the space between the cylinder, between the piston, liner, and the first ring. Piston, liner, and the first ring. I hope you have a very clear vision because we have already discussed in the class and you have done some labs also. So that is a very major crevices available in the combustion chamber. So particularly in the SI engine, what is the problem? When in the SI engine, it's a fuel and air, both comes into the combustion chamber. Okay, I'm assuming it is a PF5 carbureted engine. So during the compression stroke, when the pressure and temperature, particularly the pressure, is going to increase inside the combustion chamber, and then what will happen? The mixture will force into the small crevices. Okay, and when the combustion starts after the spark, then the pressure and temperature further is going to be increased inside the combustion chamber, and what will happen? That again the unburnt hydrocarbon will forced into the small crevices or small volumes wherever it is present in the combustion chamber. Now, when flame will reach at the door of crevices, it has a two options. Either it will propagate into the small volumes in on small crevices and it will consume all the combustion unburnt hydrocarbons, or it will disengage at the door of the crevices depending upon the what is thermodynamic conditions and depending upon the whether there is enough space, because it also depends upon the gap whether the flame will enter into or not. So suppose because of the any reason the mixture that is in the crevices is not consumed during the your primary combustion. So what will happen during the expansion stroke? When the pressure inside the combustion chamber falls below then the pressure into the crevices, then the unburnt hydrocarbon will reverse back into the main combustion chamber. And then again, it depends on the thermodynamic conditions, pressure and temperature at that time and the oxygen availability. There might be possibility that it will oxidized partially, fully, or it will not oxidized, and then it will be one of the source of the hydrocarbon emissions. That is what it is written on the first line. There might be also possibility that engine oil may participate into the combustions depending upon the conditions of the combustion chamber. Okay, it is a long chain of the carbons and fully combustion is not going to be possible within the given time, and what will happen, it will also form the source of the hydrocarbons, or because of the any reason. Okay, if there is a sudden or bulk quenching is going to be takes place of the flame because of the transient conditions, okay, or because of the any failure in the communication between the several sensors, then that might be also one of the source of the hydrocarbons, but it is only for the transient mode conditions. Okay, but the crevices and then all these things, these are the main is the main source of the hydrocarbons over the entire operating conditions of the engine. So the NO is forms because of the high temperature inside the combustion chamber and the oxygen availability of the oxygen. CO forms because of the rich air-fuel mixture, but it may get further oxidized depending upon the oxygen availability in the combustion chamber. SC formation, hydrocarbon formations, hydrocarbon emissions is main source of the how efficiently combustion is taking place inside the combustion chamber. Okay, any question here? If not, then once more, this is one of the very important curve that you need to understand, or you can find it out in any book. This is a really very important curve. I have taken it from Harvard book. Just see that this curve. What it is on the y-axis, it is the concentration of the emissions, pollutants. It's not be quantified here. On the x-axis, we have equivalence ratio. Okay, phi. So you can see phi is equal to 1. We know very well it is a stoichiometric. Once you go towards the left hand side, then what will happen? Phi will be less than 1 and it is called lean mixture. In the right hand side, phi is greater than 1 and that is called rich mixture. That we have already discussed, you know very well. So what this curve is showing to you, it is showing that how the pollutants varies with respect to the equivalence ratio. It means if I am conducting the experiments, okay, at one time, suppose my engine is running at phi is equal to 0.9, then what are the SC and NOx or CO is coming out? Then I will change the operating condition and engine will run at stoichiometric combustion, that is phi is equal to 1. Then I will read it, take the value of the different pollutants or in the richer side conditions. And that's the way it has been done, the experiments and plotted here. Now, can you tell me with this curve that where do you want to run the engine so that you can have lower pollutants in the exhaust? If you look very carefully, you will find it out that the pollutants have very complicated relations with respect to the equivalence ratio. As far as the NOx emission is concerned, what we can see that the NOx is very peak or NOx is high at slightly lean mixture. At slightly lean mixture, the NOx emission is the highest, and if from that point, let us suppose it is 0.95, if you go either in the left hand side or right hand side, the NOx emission is going to be reduced. So if our intention is to reduce the NOx emissions, what we need to do? We need to just avoid this window. We need to avoid the window of this equivalence ratio, and then we can have a NOx emissions. But it is not as so simple that just to go 0.9 or 1.1 and the NOx emission is really very lower. But the question is, what is going to be happen for the SC, CO, or the your performance of the engine? If you see the CO is very less, even up to the, we can say up to the equivalence ratio 1. Okay, but after that it is increasing. SC emissions, you can also see that when the engine is running towards the richer sides, then what will happen that not all the fuel is going to be oxidized and the part of the hydrocarbons may escape from the primary combustion and it will form the pollutants, and therefore the SC emissions is increasing as we are going towards the richer sides. In the leaner sides, what happens that when we are going to the lean sides, then it will have enough oxygen, fuel, and it is burning out. But if you further lean out, then what happens? It is going to be increased once again. This increase may be not enough thermodynamic conditions, okay, or probably it is not a combustible mixtures. Because of that, the misfire or partial combustions may take place, and that will cause for the increase of SC emissions if you lean too much of the air fuel mixture. As far as the CO is concerned, okay, in the richer sides, again, it will form the CO intermediate products. it will not find the enough oxygen to convert it into the CO2, and the CO emissions will be high. In the linear side, what will happen? That even if CO is formed, there will be enough oxygen and it will be converted into the CO, and therefore in the linear sides the CO emission is very less, but as the fuel is becoming rich and richer, the CO emissions will also increase. What is the case of NOx emission? As we discussed just in the previous slides, formation of NOx is going to be dependent on the oxygen availability and the temperature. If you remember, at one time, sometimes I have made a statement that the highest temperature that we can get it when engine is running at slightly rich mixture. Okay, but you can see here the NOx emission is not occurring where the temperature is the maximum, but it is occurring in a slightly lean mixture. Why it is happening? That if the suppose the engine is running at 1.05 equivalence ratio or slightly rich mixtures, the temperature will be very high, but what will happen? The oxygen is not going to be there because in the richer sides, so the NOx emissions will not be at the same equivalence ratio where you are getting the maximum temperature. In the slightly leaner mixture, temperature is no doubt is slightly lower than the what you will get when the engine is running at 1.05 equivalence ratio, but it will be slightly less when engine is running at around 0.95 equivalence ratio, but it is too high, and the oxygen is also going to be available because of the leaner sides, and therefore the lean mixtures, NOx emissions will be highest at this point. When you will go towards the richer sides, what will happen? Temperature and the oxygen both is going to be reduced, and the NOx emission is going to be reduced. In these sides, again, oxygen will be available, but since it is a linear mixture, and what will happen? There will be no temperature, enough temperature, and NOx emissions will be further reduced. So, what I'm trying to say with this curve, that it is not so simple to choose any one particular value of the equivalence ratio to get the pollutants, lower pollutants, and we need to maintain the performance also. It's that therefore I have made several statements that engine is or IC engine is such a dynamic machine that if you change one parameter, it is going to affect almost all the output parameters. Some of them may go into the favorable changes, some of them will go completely in the opposite directions, and then whenever we want to change parameter, it's require a huge amount of the analysis, and then we need to find it out as some intermediate step where the NOx can be reduced, where all the pollutants can be reduced up to the limit without affecting or slight compromise with the performance emissions. So this curve is particularly, it has been drawn for the SI engine, okay, and this one is for the CI engine. There is not too much difference between as far the technical discussion is concerned. The reason for both, only the difference is that between these two graph you can see in the x-axis because SI engine can run at a stoichiometric or slightly lean or slightly rich mixtures. So therefore, you can see the x-axis is covering the lean and rich mixtures. But when we are going to discuss about the CI engine, what we have discussed? We have discussed that the CI engine always run towards the linear sides. Even at the high speed and the high load condition, it is almost about to touch the phi is equal to 0.8 or 0.9. Reaching at 0.1 is probably it is not. It's never or it's not. It not doesn't run on phi is equal to 1. So therefore, we cannot display this curve, the y-axis, up in the reach or in the stoichiometric or in the richer sites. It always covers only the linear sites. The rest of the things is the same descriptions that how the NOx, SC and CO. CO, since it is always runs into the linear side, see the CO is always, it's almost like a flat straight line. Other than that, NOx has the same story, SC has also same story. Okay, any questions from your sides up to here? Any question regarding pollutant formation or the pollutant emissions with respect to the equivalence ratio? If not, then okay, that's very, very good. Let us move to the next slides. All these curves I have taken from the Harvard book. Okay, I am already explaining almost everything, but as far as the more material or understandings, you may read the book once again so that it should be completely clean. But anyway, I'm describing and covering most of the things. What this curve is showing you here, this is for the for the SI engine and the CI engine. With respect to the air fuel ratio, the same story that we have already discussed, but this is only for the showing for the specific oxides of nitrogen, that is NO and NO2 for the SI and CI engine. So this left hand side y-axis, it is representing the NO emission, and the right hand y-axis, it is representing for the NO2, and the x-axis we have a air fuel ratio. As I told you, now see the concentration. When in SI engine, where the NO emission is coming in terms of the thousand and thousands, okay, 2000, 3000, 4000. But if you see the NO2 concentration, I mean, over the entire period of the air fuel ratio, it is hardly 50, 60 or 70 ppm it is coming. And based on that, I made a statement previously that NOx in SI engine, we can say it is nothing, but it is mainly NO. NO2 contribution is almost nothing. So, however, when you can see for the SI engine, okay, what is happening? This is NO2 by NOx. It is the ratio of NO2 by NOx percentage, and you can see that depending upon the different speeds, these are the rotating. These are the indicating the different speeds versus the load on the engine. What you can say, see that this ratio, it is going up to the 30%. So we cannot make a statement in case of the diesel engine that NOx is only NO. It is not like that. It is a mixture of NO plus NO2. But in SI engine, we can make a statement that NOx is nothing but almost it is a NO. Okay. Now, one of the very important technology that we are going to discuss right now. Yeah, I think we have enough time. That is called exhaust gas recirculation, EGR. Okay. At this point, we need to discuss these things. We discussed that what is the root cause for the NOx formation. The root cause is the temperature above then critical values, and then at that point availability of the oxygen. These are the two regions. Because of that, nitrogen available in the oxygen will participate into the combustion and it will form NOx. There's a famous mechanism, okay, I think you should know, that is called Jaldevic mechanism. Jaldevic mechanism. When the temperature and the oxygen availability will be there, then how the nitrogen will react with the oxygen atoms and molecules to form the NO and NO2. For that, the Jaldevic is the name of the scientist who have developed the kinetics to form the NOx. So NOx formation is mainly follows the Jaldevic mechanism. There is 3-4 step of the equations. You may find it out in the Harvard book if you have a much interest on the kinetics of the NOx formation. So that is the reason for the NOx formation, the temperature and the oxygen. Temperature should be higher than the around 2000 degree Kelvin. Now, if once we know the root cause of the NOx formation and we want to reduce the pollutant formation, particularly the NOx, what we can do? We have two options for all the pollutants. Our main objective is that when the exhaust goes out to the atmosphere, before that we need to do something so that the exhaust should be clean as per the emissions regulation. That is the minimum requirement. That is the minimum requirement, that before going out to the atmosphere, exhaust should follow the emissions regulation. To achieve that target, at least we have two options. What are the we have two options? One, that during the combustion inside the combustion chamber, not allowed to form the pollutants. We need to optimize the parameters, design the combustion chamber, or do whatever you want to do so that the pollutants should not form or up to the maximum values. Okay, so that when during the exhaust, when the exhaust goes out to the atmosphere, it must fulfill the emissions regulation. That is, we have one pathway. The second path, but in this pathway, what is the demerit? Demerit is that when we are going to concentrate or we are going to control the emissions only through the optimization of the combustion, then we have to compromise a lot with the performance and power output of the engine. And that is not a good product. Maybe your vehicle is fulfilling the emissions, but it has not enough power, the fuel consumptions, the performance is very bad. So obviously such kind, it is not a good option. The second thing is that, the second option is that let the pollutant forms inside the combustion chamber during the combustion as much it is forming, and so that we can twin our parameters to maximize the power and the performance of the engine. And we are not taking care about the pollutants, let it form inside the combustion chamber. Then during the exhaust stroke, when the exhaust is coming out into the exhaust manifold, then the exhaust manifold itself, we need to do some sort of the chemical treatments so that before leaving going out to the atmosphere, the pollutants should be reduced to the up to the limit at least, so that we can fulfill the emissions regulation. That is our second option. Second option is also, it is not too much viable because we have very small time and our equipment, our chemical treatments, whatever you want to do, it has to be very robust, and also it is a costly, also it is going to create some back pressure, and then it will affect the combustion. So the second options, whatever we are talking about, that to do some sort of the chemical treatment to reduce the emissions. If you are following any sort of the technology to reduce the emissions in the exhaust manifold, that technology is called exhaust after treatment. Exhaust after treatment. So if that you are utilizing technology to or you are using the technology in the exhaust manifold in order to reduce the pollutants through some sort of the way, whatever you want to do. We will discuss one of the lecture we have on that, on the exhaust after treatment. This is also, we cannot rely only on the after treatment technology, neither we can dependent only on the in cylinder pollutant formations. We have to utilize the both. Partially we need to reduce the emissions inside the combustion chamber itself and maximize our power output, and then whatever the emissions are coming out in the exhaust manifold, we need to do some after treatment technology so that when the exhaust goes out, we can fulfill the emissions regulations and simultaneously we can have a very good performance of the engine. One of the technology to reduce the NOx pollutants inside the combustion chamber itself is called exhaust gas recirculation, EGR. So what is EGR? EGR is a technology that is used to reduce the NOx formation inside the combustion chamber itself. EGR is a way, or it is a technology through which we can reduce the NOx formation inside the combustion chamber itself. From the beginning itself, from the probably the Bharat Norms 2 itself, we are using EGR. Till EGR Bharat Norm 2, Bharat Norm 3, it is possible to achieve the NOx, or even 4 also, BS4 also. It was possible to achieve the NOx legislation only with the help of the EGR. BS norm 6 in some of the vehicle, okay, particularly the heavy vehicle, it is not possible, or it's not favorable to control the NOx emissions only through the EGRs, but we need to do some sort of the after treatment technology also. Okay, but right now we are going to discuss about EGR, how the EGR can reduce the NOx formation inside the combustion chamber itself. If we want to reduce the NOx formation inside the combustion chamber itself, the thumb rule is that we have to somehow reduce the temperature. We have to reduce the temperature. Oxygen availability, probably it is not a good option, because then in that case SCCO may be not be oxidized. So if we can do something so that the temperature, the rise or peak temperature itself can be lowered down, then the NOx formation inside the combustion chamber can be controlled. In fact, EGR do the same things. First of all, let us understand what is the EGR. Exhaust gas recirculation. Name itself, it is saying that what is the EGR. This is exhaust manifolds. You can see this is pipe 3. Okay. We are tapping part of the exhaust from the exhaust manifold and we are recirculating it to the intake manifold. So in the intake manifold, it is a mixture of fuel, air and exhaust gas in case of the SI engine. Otherwise, it will be exhaust and air in case of CI engine. So whenever I was trying to explain the working principle of the SI and CI engine, now you can imagine that how slowly we have changed our statement over the time. Initially, during the ideal cycle, we understand that there is a gas, only the air is coming. And then we go into the further closure, we saying that it is a only fuel and air coming inside the combustion chamber. Now we are talking about it is a fuel, air, and the exhaust gas also. So the exhaust gas recirculation is nothing but we are circulating the part of exhaust gas from the exhaust manifold and bringing into the intake manifold. So during the intake stroke, it is a mixture of fuel, air, and the exhaust gas will come into the combustion chamber. In case of the SI engine, okay. So fifth is a kind of the regulator, okay, controller, that how much exhaust EGR we want to bring into the intake manifold. We can bring it whatever you want, depending upon 1%, 2%, 5%, 20%, 30%, whatever. What happens that exhaust gas EGR, okay, exhaust gas is nothing but it is a mixture of so many gases. If you see, okay, leave it like that. The heat capacity of the exhaust gas is higher than the air. The heat capacity of the exhaust gas, okay, particularly the carbon dioxide, has a higher value than the air. So when the part of the EGR is going to mix with the air, what will happen? It will increase the heat capacity of overall mixture. We are giving the same amount of the energy, okay, but only thing is that because of this EGR mixture, the heat capacity of the mixture has been increased. What will happen? For given same amount of the heat, if the heat capacity has been increased, then the rise in the temperature will be lower down. That is the same principle it is used into the EGR to reduce the temperature and it will reduce the emissions. Several people can say that once we mix the EGR, then oxygen availability is going to be reduced because it is reducing, it is replacing the partial oxygen or partial air. Yes, these are the possibility are there, but what is the important thing is that when we will do the experiments with EGR, we will find it out that a small fraction of the EGR is not going to affect considerably into the performance of the engine, but it is significantly reducing the NOx emission. So it's a good trade-off. But if you increase the fraction of EGR too much, the engine performance is going to be affected because then we are going to have a scarcity of oxygen concentration itself. And as I told you, when we are taking the overall system engine, then our objective is not only to reduce the NOx emission. When we will discuss about the soot emission, then what will find it out? If the temperature inside the combustion chamber itself is lower, then the soot will not get enough temperature to oxidize it, and the soot emissions may increase. Yes, it is. The soot and NOx has a completely different opposite in nature. If you reduce one pollutant, NOx, soot will go up. If you reduce the soot, NOx will go up, because of they are completely in a different nature. But a small fraction of the EGR. Now, how much is called a small fraction? It depends on how much you want to tolerate, depending upon the other parameters. 5%, 10%, 20%. It depends upon your optimization and calibration of the engine, operating condition of the engine. Okay. In that way, we can control the NOx emissions up to the limit. Any question? So EGR is used to reduce the NOx emission or reduce the formation itself into the combustion chamber by lowering down the temperature, because the heat capacity of the exhaust gas is higher than the air. So overall heat capacity of the mixture increases. So for given heat, the max rise in temperature is going to be lower down. That is what the basic concept. If you have any questions, then please ask.
So is EGR used in all automobiles, or is it like a high-end technology?
No, EGR is used all. I'm not saying in the two-wheeler, but in the four-wheeler, all sort of the four-wheelers. You just trace it, go and see the exhaust manifold. You can find it out. The exhaust and the intake manifold has been interrelated with one of the pipes, and in between there is a small equipment is attached, because that is controlling the amount of the EGR. In also, as I told you, this is the basic uh, device that has been used initially from the BS norms 2 itself, particularly in the passenger cars. So it is now, except I'm not leave it about the two-wheeler, but other than that, all the vehicle, bus, truck to four-wheelers, passenger cars, EGR is the basic concept, basic technology that is used. Anything else?